All right, here we are for AP Physics Impulse Momentum Problem 2. It says two blocks of mass m and 3m are placed on a horizontal frictionless surface. Light spring is attached to one of them. They're pushed together, crushing the spring between them. And when you let go, they're going to spring apart. With the block with mass 3m ends up going to the right at 2. What's the velocity of mass m? And find the energy that was stored in the spring if m is 0.35 kilograms. So here we go. So I'm going to start with a little sketch. So I've got maybe my little track, and I've got two carts. And let's see here. There's a spring between them that's going to start off all crushed down in between them. Okay. Okay, those two carts. Now they tell you that the end, the 3m one is going to go to the right at 2. So this guy, maybe he's got some extra masses loaded up on him. So he ends up weighing triple what this guy is. 3m and m. All right. And at the start, they're sitting still. That's the before picture. A lot of times we'll draw like a before and an after when we do momentum calculations. Afterwards, I know that this guy is going to end up rolling to the right. Okay, and they tell us that the 3m guy is going to be going to the right at 2 meters per second. Okay, now at the start, the total momentum was 0. So if this part gains momentum to the right, treating it as a combined system, you know, this guy's got to gain momentum to the left, right? So the total momentum stays the same. So this guy, all right, perhaps with the spring still attached, right? But spring is no longer compressed, okay? It's going to end up rolling back away the other way, right? All right, so that's what it looks like, start and end. And you say, okay, now we want to find the velocity this one takes off to the left at. Okay, so what I'm going to do is first I'm going to do a quick conservation of momentum thing. You say, if I treat both carts as my system, then remember that momentum is an impulse are vectors. I'm just going to worry about horizontal direction. I know there's like gravity down and normal force up from the track, and those are actually going to balance out, so there's no change in vertical momentum. Horizontally, if I treat it as a combined system, there's no outside force left-right. I'm going to assume that this is frictionless. Oh, it says horizontal frictionless surface. So there's no change in momentum then. If there is no outside impulse, because there's no horizontal outside force, then the change in momentum is going to be 0. And that means the initial equals the final, because change, the final minus the initial. So back, they're equal. And so I can say the initial momentum equals the final momentum. Now, in this case, they start off at rest, right? At the start, velocity is 0 for both. So that's going to be 0 momentum at the start. At the end, I'm going to have this 3m guy going at 2 meters per second and m going at some unknown velocity. So at the end, my final is going to be, you know, m times that mystery velocity plus 3m going at 2. Do you know what I mean? Yeah. And so if I do that out, you say, solving for that v, I can divide. Both terms have m in them. So I'm going to have v is -6 meters per second. Okay, you see that makes sense. A third the mass, it'll have triple the velocity. That makes sense. So the mv this guy gains is equal to mv that guy gains. Okay, so that's it. So that's it for part A. Part B, they'd like to know how much energy must have been stored up in the spring. You say, we're going to presume that all the energy that was stored up in the spring is converted here into the kinetic energy of the two carts rolling. So doing the great big conservation of energy equation might look like this. I'm going to make my system be both carts, and I'm going to throw the spring in there too. So that means now I can have a delta U elastic potential energy in the spring. Now there are no other horizontal forces acting here doing work. So it's just going to be that final kinetic energy. Now I'm going to have 2 final kinetic energy terms. I've got 2 things moving. So I have 1/2 m times its final velocity squared plus 1/2 3m times its final velocity squared. Its final velocity is 2 squared. The velocity of this guy, we just solved that it was 6. Well, negative 6. All right. 2 squared is 4. At this point, you say, hey, look, we're trying to solve for the energy that was in the spring. Oh, they told us the masses, didn't they? They said, hey, by the way, the mass is 0.35 kilograms. So if I put that in there, I'm going to have 1/2 0.35 times negative 6 squared. That's going to be 36. Plus 1/2 times 3 times 0.35 times 4. That sounds like time for the calculator. Times 0.35 times 36 plus 0.5 times 3 times 0.35 times 4. 8.4 joules is what I'm getting. You know what, this is plus the change in the energy in the spring. Sorry about that. Which would be U spring final minus U spring initial. But at the end, the spring isn't crushed anymore, so there's no energy in it. So that's really just minus the energy in the initial. I can move that initial energy over to the other side. So then here's my U spring initial is 8.4 joules. That's what I was trying to find. There we go. Got it. And that is part B. Yep. By the way, some assumptions we're going to make when we have collisions with springs. Imagine I had something crushing a spring and I let go, right? And that spring is then going to launch that object off, right? Does all of the energy go from the spring into the kinetic energy, the guy it's shoving? You're like, well, no, I know, because the spring goes boing, right? Clearly, the spring's still wiggling around. There's energy still in the spring. We are always going to assume that that energy transfers completely to the other object. We're going to basically kind of ignore, say the spring's mass is so small that that motion of the spring wiggling around is small enough energy to ignore. Okay, just side note, that's an assumption we make in spring problems. Okay, that was problem 2.